Modern industrial warehouses are a chaotic symphony of moving parts. Human workers and heavy machinery constantly weave around obstacles in a high-traffic environment. We've built highly capable robotic arms to handle the heavy lifting in these spaces, but traditionally, those arms are physically bolted to the factory floor, strictly limiting where they can be useful. On the flip side, mobile robotic carts transport goods, but they often rely on rigid navigation, blindly following a painted line or magnetic strip, with zero ability to adapt if their path is blocked. The ultimate challenge for modern automation is bridging that gap. We need a single machine that can freely navigate unpredictable spaces and perform precise physical tasks once it gets there. Enter the Husky UGV by ClearPath Robotics. It's a rugged, all-terrain base platform explicitly designed to be customized, acting as the heavy-duty foundation for complex robotic solutions. True factory automation requires bringing siloed tasks together. By merging mobility and manipulation into one autonomous system, we can create a machine that adapts to the workspace, rather than forcing the workspace to adapt to the machine. Before it can do any work, the robot needs to understand its environment. It starts with the blank Husky chassis, a heavy-duty framework ready to be outfitted with sensory organs. The immediate priority is outfitting it for tight, structured warehouse aisles, which requires a specialized indoor autonomy package. LiDAR units mounted on the front and rear shoot out continuous two-dimensional planes of light, instantly mapping the flat surroundings to prevent collisions. To understand momentum, an inertial measurement unit detects physical forces, telling the machine exactly how fast it's accelerating or turning. But an indoor map is useless once the robot rolls out the loading bay doors. Navigating expansive, unstructured outdoor environments requires an entirely different sensory approach. For global positioning, two GPS antennas paired to rear receivers process satellite signals to pinpoint the robot's exact location. To see outside terrain, a massive VLP-32C sensor fires 32 continuous laser beams in a 360-degree circle, generating a detailed, three-dimensional view. By combining flat 2D maps, internal inertial tracking, global satellite positioning, and 3D spatial scanning, the robot builds a comprehensive view of reality. It's never blind, whether it's rolling under a warehouse roof or out in an open yard. Knowing where to go is only half the battle. Once the Husky arrives at its destination, it has to physically interact with the world using the manipulation payload mounted directly to its front deck. This specific build uses a UR5E robotic arm. It offers a 5-kilogram lifting capacity and a wide range of articulation to handle industrial parts. At the end of that arm is a 3-fingered grubber. Because you can control each digit individually, and because they utilize force feedback, the robot can securely grasp fragile objects without crushing them. Driving this hardware requires taking the bulky external control boxes normally associated with robotic arms, tearing them down and integrating the bare processing boards directly inside the chassis. Inside, two distinct computers split the workload. One runs autonomy calculations, feeding data to the main computer, which uses a dedicated GPU to process high-resolution stereo camera visuals. Powering this intense computing, the sensors and the robotic arm requires a massive upgraded lithium battery. Advanced physical robotics is ultimately an exercise in localized computing. An industrial arm is useless in the field without an intricate internal architecture to interpret the environment and supply the power to move. When all of these systems are connected through a unified software ecosystem, the result is a fully autonomous machine ready to deploy directly into a live industrial setting. Picture the robot actively navigating an outdoor loading yard. It relies on its satellite GPS for heading and localization, while the 360-degree LiDAR maps the terrain to plot a safe path around cargo containers. As it moves indoors, the system seamlessly transitions. It drops the satellite link and relies entirely on its front and rear 2D LiDARs, using them to map the immediate aisle and successfully dodge a human driving a forklift. Navigating perfectly to its assigned workstation, the robot precisely aligns its chassis parallel to an active, moving conveyor belt. Using the visual feed from the stereo camera, the mechanical arm tracks its target, reaches out, and dynamically secures a complex metallic component straight off the moving line. By successfully integrating advanced spatial perception, localized dual computing, and delicate physical manipulation into one unified platform, machines like the Husky solve the problem of rigid, stationary infrastructure. They offer a truly adaptable path forward for modern factory automation.